Welcome to a series of lectures called Class, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair for glass and glass ceramic. The purpose of these videos is to give background information on selected topics of class lectures at my chair, and the video series are not based on a structure and the sequence of the lectures. The topic for today's video is the principle of combustion calculation. As explained in a previous video, the actual energy required, H in, is the total energy that needs to be delivered by the combustion process to melt the glass. It comprises of the exploited heat and the heat losses. And if the efficiency of the glass furnace is known, H in can simply be calculated by dividing the exploited heat with the efficiency of the furnace. H in can also be calculated with the help of a combustion equation. A simple example is given here, in which methane is burned with air consisting of approximated 80% nitrogen and 20% oxygen to CO2, water and the nitrogen, which does not take part in the reaction. So if one knows the gas consumption of a furnace, for instance per ton of glass, and the lower calorific value of the gas is known, H in can be calculated. It has to be emphasized that we here only consider stoichiometric combustion. So if we burn air with methane, we only get CO2, water and nitrogen, and if it's an over-stoichiometric combustion, some oxygen left over. However, if the temperature of the combustion process increases, many other species can be generated in a combustion, for instance, like hydrogen, carbon monoxide, or even HO and H radicals. For the case that we consider a full stoichiometric combustion, let's have a look on the combustion calculation. This equation here is a general equation for the combustion of any oxygen, hydrogen and carbon containing substances. So you can just fill in the numbers of the respective atoms in your molecules and readily calculate the CO2 and the water that is generated in this stoichiometric combustion process. Now the important question is, what does a combustion equation basically tell us? First, a combustion equation tells us the energy input, the amount of energy that is brought into the combustion chamber, certainly provided the lower calorific value of the process is known. The second is the combustion equation gives us the amount of air or oxygen that is required for the stoichiometric combustion. Third, the combustion equation can tell us the maximum temperature that can be achieved. We are considering here adiabatic conditions only. And fourth, it tells us the radiation properties of the flame. For instance, in that case here, when we consider a general combustion, we have as radiative molecules CO2 and water. The nitrogen, if we consider air combustion, does not take part in any radiation properties because it's an athermic molecule. Also, the combustion equation tells us directly the molar ratios of the respective gases that are taking part in this combustion. And if we assume the ideal gas law, this also equals the volume ratios of the respective gases. Because the combustion processes we are considering here are taking place at really low pressure, it is absolutely okay to consider the ideal gas law. If we specify the combustion equation, for instance, alkanes, we come to this equation. And if we specify the combustion equation for alcohols, we come to this generalized equation. These two equations are basically some simplification of the previously shown equation. Now, if we consider the combustion for alkanes, for instance like methane or ethane, you directly get the fuel quantity from the combustion equation that is taking part in the combustion. This is MF. If now the lower calorific value is also known, for instance from tabulated values, you can directly calculate the total energy input into the furnace by simply multiplying the fuel quantity with the lower calorific value of combustion gas. Just some words on the lower calorific value and the corresponding upper calorific value. The lower calorific value refers to water being still in gaseous form, so it's not condensated. The upper calorific value additionally draws energy from the condensation of the gaseous water into the liquid water. So the upper calorific value is always higher than the lower calorific value. However, because in glass furnaces the temperature of the off gas is usually way above 100 degrees Celsius because of certain filter requirements later in the process, we always consider the lower calorific value. Let's have a look at a simple combustion calculation. In this example here, the combustion process is methane in air, giving us CO2, water and nitrogen. You can now simply calculate the atoms and equalize the equation. However, I would like to show you a procedure that is more versatile and that can be applied into any combustion process. For this simple combustion process, we first determine the oxidization and the reduction reaction. The oxidization reaction is carbon is oxidized from -4 to +4, giving 8 electrons. The reduction process is oxygen ±0 is taking up 2 electrons, yielding oxygen -2. Now, to balance these two equations, you simply have to multiply the lower equation here with 4 and the upper equation with 1, resulting in 2 oxygen, giving 1 CO2, 2 water, because the nitrogen is not taking part in the reaction and the ratio between oxygen and nitrogen in air is roughly 1 to 4. You need 8 molecules of nitrogen, resulting at again 8 molecules of nitrogen on the product side. Now, this is a quite simple combustion equation. How does it look like if the combustion process is more complex? Let's assume we have an air number of 0.925, which means that in the case of an oxygen combustion, the available amount of oxygen is only 92.5% of the stoichiometrically needed amount of oxygen. So we have an under-stoichiometric combustion. We do not have enough oxygen to combust all our combustion gas. Now let's again consider the combustion of methane with oxygen, now with a pure oxyfuel combustion. And the air number of 0.925 would mean that we have, and because we need to have full number of atoms, you have to recalculate the numbers. So it would mean for 10 molecules of methane, we would have 18.5 molecules of O2, so 37 atoms of oxygen. If it would be a stoichiometric combustion, for 1 molecule of methane, you would need 2 molecules of oxygen, or for 10 molecules of methane, you would need 20 molecules of oxygen. And again, because we have here an under-stoichiometric combustion with an air number of 0.925, we end up with, instead of 20 molecules of oxygen for 10 molecules of methane, with 18.5 molecules of oxygen. Let's now write down the combustion equation in terms of oxidization and reduction. We have first the fixed number of 73 atoms of oxygen ±0. That is reduced to oxygen -2, giving us a total of 75 electrons. For the oxidization, because it's an under-stoichiometric combustion, we first consider the oxidization of the carbon in the methane at -4 to carbon +2 in carbon monoxide. For this reaction, for each carbon atom, we need 6 electrons. For the reduction, we have the fixed number of 74 electrons. And now we combust all the carbon from -4 to +2. For this process, we need for 10 carbon atoms, 60 electrons. And with this, we have all the carbon from -4 in the methane converted to carbon +2 in the carbon monoxide. However, in that case, we still have 14 electrons left. Now, these 14 electrons can be used to combust the carbon monoxide further to CO2. The question now is, how many molecules carbon monoxide can we convert to carbon dioxide with these 14 electrons left? And certainly the number is 7. So we end up with additionally 7 molecules of CO2. These 7 molecules CO2 certainly are subtracted from the 10 molecules of carbon monoxide, CO, and this gives us in the total equation 7 molecules of CO2, 3 molecules of CO, carbon monoxide, and then we can calculate 20 molecules of water. Now, this is the example of a more complex combustion equation. However, I have to emphasize here that equilibrium reactions can be quite complex and can be influenced by many different factors such as pressure, available catalysts, and the equation combustion here may change depending on the frame conditions. At last, let's have a look at the lower calorific value. If one wants to calculate the lower calorific value, you can simply take the density of the respective component, the specific lower calorific value of the respective component, and the ratio of that component in the combustion gas. And then you get the lower calorific value directly in terms of kilowatt hour per cubic meter, or you can directly multiply the specific lower calorific value of the respective component with the molar ratio of the component, and then you get the lower calorific value in terms of kilowatt hours per kilogram. Values for the density and the calorific value of different components can be taken from tabulated values. Here are some examples, for instance, for carbon monoxide, for hydrogen, for methane, ethane, and so on. And if you calculate the lower calorific value with this equation, you can directly use the lower calorific value again in your H-in calculation, multiply it with the amount of gas that is burned, and directly get the total energy that is brought into the furnace. With this, we are at the end of this video, and I trust it was helpful for your further understanding of glass science.